Hello and welcome back to the channel. In today's video, we're overclocking the Intel Core Ultra 5 245K processor all the way up to 5633 MHz using a Z890i gaming motherboard and Enermax AIO cooling. I'll do this by using most of the tools that I've explored in my Arrow Lake launch content. In this video, I break down the Core Ultra 5 245K tuning process into 6 unique overclocking strategies for beginners and advanced overclockers. This is the very first SkatterBencher Arrow Lake overclocking guide, so I didn't quite know how to cover all of the different overclocking strategies without taking up too much of your time. I suspect this will be a pretty long video, so please bear with me. Anyway, before we start with the overclocking, let's first have a look at the system, the benchmarks, and of course the stock performance. The Intel Core Ultra 5 245K is part of Intel's Core Ultra 200S product line, codenamed Arrow Lake. The Arrow Lake desktop processors for enthusiasts were introduced on October 24th, 2024. The Core Ultra 5 245K succeeds the 14-core Raptor Lake Core i5 14600K. It has a P-core base clock of 4.2 GHz and a listed boost frequency of up to 5.2 GHz. The E-cores can boost up to 4.6 GHz. The system we're overclocking today consists of the following hardware. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we start overclocking, of course, we have to check the performance at default settings. In the past, there was some confusion about what constitutes default settings for Intel processors. Intel defines 3 power profiles for Arrow Lake processors: baseline, performance, and extreme. For the purpose of this guide, we follow Intel's direction and rely on the performance profile for the default settings. The Intel default performance profile configuration parameters for Arrow Lake CPUs are as follows. The Intel default performance profile Turbo Boost 2.0 parameters for the Core Ultra 5 245K are as follows. And the turbo ratio limit parameters for the Core Ultra 5 245K are as follows. Here's the benchmark performance at stock. Here are the 3D Mark CPU profile scores at stock. Here are the OCCT benchmark scores at stock. Here's the AIDA64 memory benchmark scores at stock. When running the OCCT CPU AVX2 stability test, the average CPU P-core effective clock is 4999 MHz with 1.099 volts. The average CPU E-core effective clock is 4473 MHz with 1.066 volts. The average CPU temperature is 62 degrees Celsius, and the average CPU package power is 127.8 watts. When running the OCCT CPU SSE stability test, the average CPU P-core effective clock is 4992 MHz with 1.097 volts, and the average CPU E-core effective clock is 4541 MHz with 1.073 volts. The average CPU temperature is 61 degrees Celsius, and the average CPU package power is 118.9 watts. Of course, we can improve the performance by unleashing the power limits, and that's exactly what we'll do in our very first overclocking strategy. But before that, make sure to locate the clear CMOS jumper. Shorting the clear CMOS jumper will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. In our first overclocking strategy, we take advantage of ASUS Advanced OC Profile, ASUS Multi-Core Enhancement, and Intel XMP 3.0. For Arrow Lake, Intel has imposed stricter rules concerning stock behavior or the default settings. Of course, that restricts the motherboard partners a little bit in what they can do with the motherboard out of the box in terms of enabling certain settings, but it also makes a little bit more room for innovation. And one of those innovations is the ASUS Advanced OC Profile. In essence, the ASUS Advanced OC Profile sets up the BIOS so it's ready for overclocking. Not only does it reconfigure some of the parameters included in the definition of Intel's default profiles, but it also configures a number of other settings related to power saving, performance limiters, and so on. By modifying some of these parameters, you can enable higher performance. But most importantly, if you want to adjust any settings related to overclocking, you are required, it is mandatory to enable ASUS Advanced OC Profile. Intel Turbo Boost 2.0 is a technology that allows the processor to run faster than the base configuration when the processor is operating within power, current, and thermal limitations. The obvious advantage is additional performance across the board, both in single-threaded and multi-threaded applications. The Turbo Boost algorithm works according to an EWMA formula. This stands for exponentially weighted moving average. There are three main parameters to consider: PL1, PL2, and tau. Turbo Boost 2.0 technology has evolved over the past years to incorporate a lot of power, thermal, and electrical performance limiters. An easy ASUS multi-core enhancement option on ASUS motherboards allows you to unleash the Turbo Boost power limits. Intel Extreme Memory Profile 3.0 is the very new XMP standard for DDR5 memory. It was introduced together with the Alder Lake processors in 2021. It is largely based on the XMP 2.0 standard, but has additional functionality. The XMP 3.0 standard is designed with 6 sections. One global section describes the generic data that is used across all the profiles, and the 5 other sections are designed for 5 individual profiles. Each profile has a wide range of configurable fields related to voltage, frequency, and memory timings. XMP allows memory vendors such as G.Skill to program higher performance settings onto the memory sticks. If the motherboard supports XMP, you can enable higher performance with a single BIOS setting, so it saves you from a lot of manual configuration. Regular viewers of this channel will know that this particular memory kit is a little bit finicky and it doesn't run 7800 on all systems, including this one. So I had to adjust the memory frequency just a little bit to DDR5 7600 to make sure it ran fully stably. Upon entering the BIOS, the CPU boost frequency with one active P-core is 5200 MHz. The average boost frequency gradually trails off to 5000 MHz when all P-cores are active, and to 4771 MHz when all P and E cores are active. Every P-core can boost to 5.2 GHz, and every E-core can boost to 4.6 GHz in single-threaded workloads. We reran the benchmarks and checked the performance increase compared to the default operation. The Core Ultra 5 245K is the least powerful of all Arrow Lake K-SKU processors and thus not that limited by power or memory performance. That said, we still see a nice uplift across the board, primarily with multi-threaded applications and almost 10% in Counter-Strike 2. The geo-mean performance improvement is plus 3.71%, and we get a maximum improvement of plus 32.39% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU P-core effective clock is 4998 MHz with 1.102 volts, and the average CPU E-core effective clock is 4601 MHz with 1.077 volts. The average CPU temperature is 70 degrees Celsius. The average CPU package power is 137.2 watts. When running the OCCT CPU SSE stability test, the average CPU P-core effective clock is 4993 MHz with 1.100 volts, and the average CPU E-core effective clock is 4589 MHz with 1.078 volts. The average CPU temperature is 70 degrees Celsius. The average CPU package power is 128.5 watts. In our second overclocking strategy, we finally get to overclock the CPU cores. And for that purpose, I use two fundamental Intel overclocking technologies: the turbo ratio limit and adaptive voltage mode. Intel turbo ratio limit is a technology that regulates the CPU core frequency based on how many cores are active.
Intel processors usually have two types of CPU core frequencies specified: the base frequency and the turbo boost frequency. The base frequency is also known as the maximum non-turbo ratio, whereas the turbo frequency is usually referred to as the turbo ratio limit.
Turbo ratio limit is called a limit because it's not really targeting a certain frequency, but it's rather limiting to a certain frequency. Processors like the Core Ultra 5 245K actually can boost all the way up to 120x with certain parameters enabled. However, if we set a turbo ratio limit to 56x, then it doesn't boost all the way to 120x, it boosts to 56x.
The tool is pretty flexible and can be programmed for various scenarios. The ratio limits are defined in the processor's machine-specific register MSRs by two parameters: the turbo ratio limit and the number of active cores. For CPUs like the Core Ultra 5 245K, which have no more than 8 P-cores, these registers are configured from 1 active P-core to 8 active P-cores. Furthermore, on hybrid designs like Alder Lake, Raptor Lake, or Arrow Lake, which all feature a combination of P-cores and E-cores, the turbo ratio limit configuration is specified by core type. In other words, the applied ratio limit for the P-cores is independent from the limit of the E-cores. For example, on the Core Ultra 5 245K, if 2 P-cores and all E-cores are active, the P-cores will operate at 52x, even though more than 2 cores are active in total.
Note that when we are configuring a turbo ratio limit, we're not actually configuring each core individually. What we're doing is setting a frequency based on the number of active cores. Per core ratio limit is a technology that allows you to set a maximum frequency for every core individually. It's based on the technology called Turbo Boost Max 3.0, which was launched in 2016. It acts completely independently from the turbo ratio limit, meaning that you can restrict a core from boosting higher even if your turbo ratio limit would allow it.
The per core ratio limit plays an important role in the Arrow Lake overclocking process. It's not only the ratio used in the VF point configuration, but also the ratio referenced by many other ratio tuning technologies. In our case, we'll use it to restrict the cores with less overclocking headroom to boost as high as the cores with amazing headroom.
The voltage regulation for the Arrow Lake CPU cores is slightly different than on previous architectures, and that's primarily because of the introduction of the DLVRs, the digital linear voltage regulators. These DLVRs allow for much lower voltage of the CPU cores, but they still rely on a dynamic external motherboard voltage regulator as input voltage.
The external VCCIA motherboard voltage regulator, or MBVR, provides the input voltage for the individual P-core, E-core clusters, ring, last level cache, and E-core L2 cache. Each P-core, E-core cluster, and ring has an individual digital linear voltage regulator, or DLVR, sitting between the VCCIA rail and the IP blocks. That means each of the blocks can operate at its own voltage.
The DLVRs can also be bypassed, and in that case, we're running in so-called PG mode. I'll get back to that later in this video.
Each Core Ultra 5 245K P-core and E-core cluster also has its own VF curve, which is defined by 7 VF points. The first 6 VF points are factory fused, and the last point is mapped to the so-called OC ratio. Here is the aggregate P-core VF curve for my specific Core Ultra 5 245K. The voltage is about 731 mV at 800 MHz, then increases to 1.071 volt for VF.4 at 4.8 GHz, and ultimately ends up at 1.178 volt for VF.6 at 5.2 GHz. Note that each P-core has a different fused voltage for VF.6, which ranges from 1.156 volt for Core 0 to 1.203 volt for Core 3. Here's the aggregate E-core VF curve for my specific Core Ultra 5 245K. The voltage is about 671 mV at 800 MHz, then increases to 0.785 volt for VF.4 at 3 GHz, and ultimately ends up at 1.098 volt for VF.6 at 4.6 GHz. While each E-core cluster can have a different fused voltage for VF.6, for this particular CPU, it's the same at 1.098 volts. Based on the VF curve, the CPU cores request an operating voltage using the ISFIT protocol from the CPU Power Control Unit, or PCU. The PCU in turn configures the VCC-IA voltage rail and the individual DLVRs. There are two ways to configure the DLVR voltage: adaptive mode and override mode. We can configure override and adaptive modes directly in the PCU by specifying a target voltage and a voltage offset for each mode. In adaptive mode, the target voltage is mapped to a core's OC ratio. Each P-core and E-core cluster has its own OC ratio, which is defined by the per-core ratio limit. This also matches VF.7. You can configure the adaptive voltage and the OC ratio to any value. However, multiple rules enforce what ratio and voltage are actually set. Rule number 1, the voltage set for a given VF.N must be higher than or equal to the voltage set for VF.N-1. That means the voltage for the OC ratio, matching VF.7, must be higher than or equal to the voltage for VF.6. For example, let's say you've configured the P-core per core ratio limit to 56x and the adaptive voltage to 1.1 volt. In that case, the actual frequency will be 5.6 GHz with 1.178 volt, as that's the voltage for VF.6. Even if you set the voltage lower in BIOS, the PCU will override your configuration if it doesn't follow the rules. Rule number 2, for ratios between the OC ratio and the next highest factory fused VF point, the voltage is interpolated between the set adaptive voltage and the factory fused voltage. Let's say we've configured the P-core VF OC point to 56x and 1.4 volts. The target voltage for P-core ratio between 52x and 56x is now interpolated between the P-core's factory fused voltage for 52x and the set adaptive voltage for 56x.
There are several ways how you can set an adaptive voltage for the P-cores and the E-cores, including configuring them individually. However, for this overclocking strategy, I will apply a single global adaptive voltage that applies to all the P-cores and all the E-core clusters. Thermal velocity boost is a technology that exploits the fact that CPUs need less voltage to run a certain frequency when the operating temperature is lower. When the TVB voltage optimizations are enabled, the CPU will automatically reduce the voltage if the operating temperature is lower.
For example, for my Arrow Lake launch content, I collected data for the Core Ultra 9 285K to illustrate this behavior. As you can see from the data, with the P-core at 5.4 GHz, the operating voltage is 1.237 volt when the temperature is below 50 degrees Celsius. However, it increases to nearly 1.3 volt when the temperature approaches 100 degrees Celsius. If you want manual control over the operating voltage to ensure stability, like when you're trying to overclock, it's prudent, but of course not mandatory, to disable this function.
The manual tuning process for the Arrow Lake P-cores and E-cores can become quite convoluted, because really it spans a wide range of workloads and use cases, going from single-threaded light workloads all the way to all-core heavy multi-threaded workloads. I suggest that you first pick an adaptive voltage that you're comfortable with, then check what the maximum frequency in single-threaded applications is, and then finish it up by also checking what is your all-core stability like. The easiest way I find to determine what kind of an adaptive voltage I want to run is basically looking at what's the stock maximum voltage and then adding anywhere between 50 and 200 millivolt.
For example, the default maximum voltage for this CPU is 1.2 volt for P-core 3, so I decided to add 150 millivolt headroom and set the P-core adaptive voltage to 1.35 volt. For the E-cores, the maximum voltage is 1.1 volt, so I add plus 175 millivolt and set it to 1.275 volt. Note that we want full control over the effective voltage, so make sure to disable any technologies that might adjust the operating voltage, such as TVB or advanced voltage offset. After you've set your target adaptive voltage, you can find the maximum stable frequency for each P-core and E-core cluster at that voltage. The easiest way to do that is by setting the turbo ratio limit to, let's say, 60x, and then setting the per-core ratio limit to the frequency you want to test. For example, 54x for the P-cores and 48x for the E-cores. Now you can run a stress test of choice. I typically rely on the OCCT CPU stress test, which has a core cycling function built in. But you can also run a custom application like Core Cycler or pick a different stress test altogether. You can start with a 30-second quick test to first quickly find the upper limit, then longer test times to confirm stability. Finally, we need to check if the CPU is also stable in non-single thread workloads. The easiest way to do this is by running your worst case all-core workload, which in my situation is always 30 minutes of OCCT CPU AVX2 stability test. You'll typically find that the CPU cannot run all-core at the same frequency as it can run single-threaded workloads. If that's the case, simply lower the turbo ratio limit for all core workloads until it's stable. In addition to the OCCT CPU AVX2 stability test, I generally also include 3 other workloads during all core testing: Y-Cruncher, Cinebench R23, and AI Benchmark. While these 3 tests are no replacement for the worst case stress test, they highlight different kinds of instabilities, usually related to transitive loads. For example, Cinebench R23 seems particularly useful to detect AVX-related all-core instabilities. An AI benchmark typically detects if the per-core ratio limit is too high. With 1.35 volt adaptive voltage for the P-cores, I could increase P-core 0 and 1 to 5.5 GHz, P-cores 2 and 3 to 5.6 GHz, but P-cores 4 and 5 to only 5.3 GHz. I'll get back to P-core 4 and 5 later in this guide. With 1.275 volt adaptive voltage for the E-cores, I could increase both E-core clusters to 4.9 GHz. Upon entering the BIOS, the CPU boost frequency with one active P-core is 5600 MHz. The average boost frequency gradually trails off to 5300 MHz when all P-cores are active and 5071 MHz when all P and E-cores are active. In single-threaded applications, 2 P-cores can boost to 5.6 GHz, 2 can boost up to 5.5 GHz, and 2 to 5.3 GHz. Every E-core can boost to 4.9 GHz. We reran the benchmarks and checked the performance increase compared to the default operation. As we significantly increase the operating frequency of both the P-cores and the E-cores, we also see a decent performance uplift across the board as games, single-threaded and multi-threaded workloads all benefit from our overclock configuration. The geomean performance improves by another 3.65 percentage points, and we get a maximum improvement of plus 34.35% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU P-core effective clock is 5291 MHz with 1.252 volts, and the average CPU E-core effective clock is 4901 MHz with 1.277 volts. The average CPU temperature is 90 degrees Celsius. The average CPU package power is 209.1 watts. When running the OCCT CPU SSE stability test, the average CPU P-core effective clock is 5291 MHz with 1.252 volts, and the average CPU E-core effective clock is 4891 MHz with 1.277 volts. The average CPU temperature is 91 degrees Celsius. The average CPU package power is 199 watts.
In our third overclocking strategy, we're overclocking the data fabric, which consists of the ring, the NOC in the NGU, and the CPU die-to-die interface.
The ring fabric provides the data fabric interface between the various compute IP blocks in the compute tile, the last level cache, and the SoC compute D2D interface. The ring reference clock frequency is generated internally by the CPU PLL. This clock affects all IP blocks in the compute tile, including the P-cores, the E-cores, and the ring. This PLL can be linked to the SoC PLL when you run it in synchronous mode, or work independently if you run in asynchronous mode. The reference clock is multiplied by the ring ratio to achieve the final clock frequency. The default ratio is 38x, which yields a 3.8 GHz operating frequency. As we covered before, the voltage regulation of the ring is more complex than previous generations of Intel Core processors due to the introduction of the DLVR. The Core Ultra 5 245K ring has its own VF curve, which is defined by up to 7 VF points. The first 6 VF points are factory fused, and the last point is mapped to the OC ratio. Oddly enough, while the default ring frequency is 3.8 GHz, the VF curve is actually defined up to 3.9 GHz. Here's the ring VF curve for my specific Core Ultra 5 245K. The voltage is about 818 mV at 800 MHz, all the way up to 2.8 GHz. Then it increases to 1.136 volt for VF.6 at 3.9 GHz. The voltage configuration of the ring is identical to that of the P-cores, including the adaptive and override modes, and the specific rules governing the adaptive voltage mode, which I covered at length in the previous OC strategy. NGU stands for Next Generation Uncore and is a successor to the Uncore we know from previous generation Intel processors. On Arrow Lake S, NGU overclocking is essentially NOC overclocking. The NOC fabric is the primary communication bridge between the various IP blocks on the chip, such as the memory controller, the CPU cores via the D2D, graphics also via the D2D, and so on. The NGU reference clock frequency is generated internally by the SoC PLL, however it can also be clocked with an external clock generator providing the reference clock for the SoC PLL. The reference clock is multiplied by the NGU ratio to achieve a final clock frequency. The default ratio is 26x, which yields a 2.6 GHz operating frequency. The external VCC-SA motherboard VR or MBVR powers several parts of the SoC dielet, including the NGU. Unlike the compute IP, the parts of the SoC dielet are not powered using DLVR, so power delivery is identical to previous architectures. The voltage configuration for the VCC-SA voltage rail is rather complicated, because since multiple IP blocks share the voltage rail, the VCC-SA voltage is set based on the highest requested voltage from the various connected IP blocks. The NOC has its own VF curve, which is defined by up to 4 VF work points. The first 3 work points at 11x, 23x, and 26x are factory fused, and the last point is mapped to the OC ratio.
Based on those work points, the NGU will request a certain voltage from the VCC-SA voltage regulator using the SFET protocol. But there's another way how we can get voltage on the VCC-SA rail, and that's ignore all of the SFET requests and set the voltage directly using PM bus mode. That means we basically have full control over the output voltage of the VCC-SA.
This approach is a very traditional way of overclocking whereby you set a fixed output voltage and then use an appropriate VRM load line setting, if available, to reduce the operating voltage in higher load scenarios. D2D stands for die to die. It is the interface between the various tiles on the Arrow Lake package. There are 3 D2D links connecting the various tiles on this package. On Arrow Lake, only the SoC compute D2D can be overclocked. Its base frequency is 2.1 GHz. The D2D reference clock frequency is generated internally by the SoC PLL, but it can also be clocked with an external clock generator, providing the reference clock for the SoC PLL. The reference clock is multiplied by the D2D ratio to achieve a final clock frequency. As I said, we can only adjust the SoC compute D2D frequency. The default ratio is 21x, which yields a 2.1 GHz operating frequency. The maximum configurable ratio is 40x. The external 0.77 volt VNN AON voltage rail powers several internal voltages, including the D2D interfaces. The VNN AON voltage is pretty important for Arrow Lake CPUs as it is part of the voltage multiplexer for many IP blocks, including the cores and ring, typically serving as the floor voltage in power saving scenarios.
I don't suggest increasing the VNN AON voltage above 1 volt because, well, 1, it doesn't really add that much overclocking headroom, and 2, the system can get a little bit finicky when you use high D2D frequency with a high VNN AON voltage.
Fortunately, Asus has included an option called High D2D Cold Boot Workaround in the BIOS that can help alleviate some of the booting issues with increased VNN AON voltages.
Tuning the data fabric is a matter of going through every component systematically. I suggest that you first pick target voltages for each of the components, set those in the BIOS with the default frequencies, and then increase the frequency one by one, trying to figure out the maximum stable frequency.
The initial test can be very quick. For example, I'll run a 30-second cycle of Y-Cruncher FFT component tester to find the initial upper limit for each component. When I know the upper limit, I'll set all target ratios and do longer stints of stability testing, including the introduction of other tests. I find that typically Cinebench R23, Y-Cruncher Benchmark, and Component Tester and AI Benchmark are very sensitive to data fabric overclocking.
This process might take a while, especially if you're trying to figure out what's the maximum stable frequency. Of course, once you've gone through all of your stress tests, you also want to make sure that it passes all of your benchmarks.
Ultimately, I ended up with a 4.4 GHz ring, a 3.2 GHz NGU, and a 3.6 GHz D2D. Upon entering the BIOS, We reran the benchmarks and checked the performance increase compared to the default operation. As we significantly increase the operating frequency, we also see a decent performance uplift across the board as games, single-threaded and multi-threaded workloads all benefit from our overclocked configuration. The geomean performance improves by another 1.84 percentage points, and we get a maximum improvement of plus 44.54% in PY prime. Tuning the data fabric had a minor impact on the OCCT stability test, increasing the average CPU temperature by about 3 degrees Celsius and increasing the average CPU package power by up to 9 watts.
In the fourth overclocking strategy, we try to squeeze a little bit more CPU frequency. To do that, I go beyond the standard Arrow Lake voltage limits. I make use of the granular ratios. I switch to more precise per core voltage, and I also use a static VCCIA voltage. To safeguard the processor during overclocking, Intel has, for the very first time, put very strict voltage limits on several components of the Arrow Lake package, including the P cores and the E cores.
This voltage limit effectively prevents the cores from requesting a higher voltage from the PCU. By default, the voltage limit for the P cores and E cores is plus 200 mV above the lowest VID for the P cores and the E cores VF.6. For this CPU's P core, that's 1.356 volts, and for the E cores, it's 1.298 volts. However, we can manually increase that to plus 300 mV under ambient conditions, so 1.456 volt and 1.398 volt respectively. If you try setting the limit above the approved limit, the PCU will automatically adjust it to the highest allowed limit.
Intel per core voltage allows you to set a specific voltage for each P core and E core cluster of your Arrow Lake CPU. Obviously, this is only possible when DLVR is enabled because you're configuring the DLVRs.
Similar to the global voltage mode, you can configure the per core voltage in adaptive mode and override mode, specifying a voltage for the defined per core ratio limit or across the VF curve respectively. The per core voltage implementation for Arrow Lake is slightly different than prior platforms, as each P core and E core cluster now has its own OC ratio. Functionally, that means every per core voltage is mapped to a respective per core ratio limit and thus also serves as the base voltage for VF.7. The standard rules for adaptive mode voltage, which we discussed in OC strategy number 2, still apply. As a consequence, it means that each P core and E core's cluster VF curve is truly independent, as voltage interpolation is done for each core individually. Granular ratios are a brand new overclocking feature for Arrow Lake. It adjusts the per core ratio limit by letting you set the CPU frequency in steps of 16.67 and 33.33 MHz. The granular ratios can only be configured in reference to the per core ratio limit, not as a turbo ratio limit. That's because technically the granular ratios aren't set directly, but instead downbinned from the per core ratio limit. For example, let's say you set a granular ratio of 60.16x. In that case, the per core ratio limit is set to 61x and then downbinned 5 steps of 16.67 MHz, which is 100 MHz divided by 6. That is important to keep in mind in case you're also using other ratio configuration technologies like AVX offset, for example. It is also important to keep in mind when using adaptive voltage mode because the adaptive voltage maps to the OC ratio. As we discussed a couple times already in this guide, the external VCCIA motherboard voltage regulator provides the input voltage for the VCC core, VCC atom, and VCC-R DLVR. It's a dynamic voltage that is configured by the CPU PCU based on all the voltage requests from all the different IP blocks powered by these DLVRs. However, we can also manually override the VCCIA voltage while maintaining DLVR mode. I decided for this OC strategy to try a static VCCIA voltage mode for 2 reasons. One, with the elevated voltages, the VCCIA maximum voltage jumps up quite a bit to over 1.6 volts. 2, I found that the system stability was more predictable, making it easier to eke out additional frequency. Since the maximum voltage for the VCCIA powered DLVRs is 1.45 volt, the P cores, I settled on a static VCC-IA voltage of 1.525 volt. Do note that you must also consider the VCC-IA VR load line, just like with previous architectures. I fixed the load line to level 6 to have a flatter curve across all the loads.
I follow a similar testing procedure as in OC strategy number 2 when I'm trying to figure out the maximum CPU core overclock. The only difference really is that as you get closer to the limit of the CPU cores, the amount of testing required increases quite a lot.
In the end, I could achieve 5,633 MHz for P-cores 2 and 3 at 1.45 volt, 5,533 MHz for P-cores 0 and 1 at 1.4 volt, and still only 5.3 GHz for P-cores 4 and 5 with 1.2 volt. The last two P-cores were behaving quite weirdly because the voltage limit was 1.4 volt, like the E-cores, and not 1.45 volt, like all of the other P-cores. Also, the overclocking headroom did not scale with increased voltage. So the maximum frequency is 5.3 GHz, no matter whether I set 1.2 or 1.4 volt. With 1.4 volt adaptive voltage for the E-cores, I could increase both E-core clusters to 5.1 GHz. Upon entering the BIOS, The CPU boost frequency with one active P-core is 5633 MHz. The average boost frequency gradually trails off to 5478 MHz when all P-cores are active, and to 5205 MHz when all P and E cores are active. In single-threaded applications, 2 P-cores can boost to 5633 MHz, 2 can boost up to 5533 MHz, and 2 to 5.3 GHz. Every E-core can boost to 5.1 GHz. We reran the benchmarks and checked the performance increase compared to the default operation. While the additional voltage doesn't add much P-core top speed, the additional 200 MHz for the E-cores helps lift the performance in multi-threaded workloads. The geomean performance improves by another 1.38 percentage points, and we get a maximum improvement of plus 44.30% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU P-core effective clock is 5471 MHz with 1.353 volts, and the average CPU E-core effective clock is 5001 MHz with 1.333 volts. The average CPU temperature is 97 degrees Celsius. The average CPU package power is 280.4 watts. When running the OCCT CPU SSE stability test, the average CPU P-core effective clock is 5471 MHz with 1.353 volts, and the average CPU E-core effective clock is 4989 MHz with 1.333 volts. The average CPU temperature is 97 degrees Celsius. The average CPU package power is 264.1 watts.
In the fifth overclocking strategy, I have a look at the memory subsystem to see if it has any impact on system performance. The memory subsystem obviously consists of the memory controller and the system memory, and then the system memory consists of its frequency and the memory timings. To tune the memory subsystem, I use the ASUS memory presets from the Z890 Apex from the board here behind me, and also some manual timing adjustments. ASUS Memory Presets is an ASUS technology that provides you a selection of memory profiles for a variety of DRAM ICs. Typically, these profiles will set the memory timings as well as adjust some voltages.
Not all motherboards have memory presets available. For example, this ROG Strix Z890i Gaming doesn't. Luckily, I have a Z890 Apex on hand and could copy over the timings from the Hynix 8400 1.5 2x16GB A-die profile. For your reference, here are the relevant timings. Of course, it's not a given that just copying the memory timings will be stable. So what I typically do is I'll copy the timings and then start at a pretty low frequency like DDR5 6000 and then slowly make my way up to check if it's actually stable. I'm aware there's a lot of discussion about what exactly constitutes memory stability, but I've always relied on 1 hour of OCCT memory stress test. To my surprise, I found that the memory was now stable at DDR5 8000. Here's my final memory configuration. After the tuning, our AIDA64 performance improved quite significantly. We got about plus 50% extra bandwidth and plus 25% extra latency by enabling XMP. By tuning the data fabric, we added a couple more percentage points of bandwidth and also improved the latency by almost 20%. The tuned memory then adds another 20% extra write and copy bandwidth while maintaining the same latency. We reran the benchmarks and checked the performance increase compared to the default operation. Tuning the memory timings and adding a little bit of frequency doesn't have the enormous impact some would expect. However, it's nonetheless interesting we get a good performance bump across the board, both in single-threaded as well as multi-threaded workloads. The geomean performance improves by another 1.42 percentage points, and we get a maximum improvement of plus 56.18% in PY prime. In the final overclocking strategy, I have a look at PG mode or power gate mode to see if it can help improve our overclocked performance. In power gate mode, all the DLVRs tied to the VCC-IA voltage rail are bypassed and the connected IP blocks are powered directly by the VCC-IA voltage rail. Power gate mode is basically how the VCC-IA voltage rail worked on previous generation Raptor Lake. And for Arrow Lake, it also works, but it's a little bit complicated. To make a long story short, when the P-cores, E-cores, and ring request their voltage to the CPU PCU, They account for a ton of other compensations. The result is that the actual voltage provided from the VCC-IA voltage rail to the IP blocks is relatively high. For example, here are the voltages with an Arrow Lake CPU running an all-core workload. We can interpret this as follows. The P-core, E-core, and ring request a voltage to the PCU to ensure it'll run 1.25, 1.15, and 1.2 volt respectively. The PCU then adds compensation for the load lines, CEP, TVB, AVX, ACLL, DLVR efficiency losses, and so on. At the end of the calculation, the PCU determines the VCC-IA voltage rail should provide 1.53 input voltage to the DLVRs.
If we were to switch to power gate mode and leave the calculation up to the CPU, it would mean that the P-cores, E-cores, and ring would have the 1.53 voltage directly from the VCC-IA voltage rail. That's pretty steep, so not ideal. Fortunately, there's another way how we can set the VCC-IA voltage rail. Ignore all of the ISFIT requests and program the voltage directly over PM bus mode. That basically means that we take full control over the output voltage of the VCC-IA voltage rail. And that's how overclocking was done traditionally. You set a static output voltage and then you use a VR load line to control the output voltage in high load scenarios, like for example, all-core multi-threaded workloads.
But before we continue, we must talk about the elephant in the room. Power gate mode will not be available for ambient overclocking in the future. Or at the very least, that's Intel's plan. The real reason is not known, but it's probably got something to do with power gate mode enabling voltages much higher than the DLVR limits. That could, in theory, cause harm to the CPU.
My opinion on the matter is pretty clear. Using power gate mode is not in-spec behavior. It voids the warranty, and you have additional risk that you might damage your processor. But whether or not to accept that risk is up to the customer. It's up to you. It's not up to Intel. You don't need anyone sitting in a cubicle very far removed from your system to tell you what you can and cannot do with your purchased product.
With that out of the way, I also want to briefly touch on why power gate mode is still available on some motherboards with newer BIOSes. To keep it short, while the latest firmware package from Intel doesn't officially allow for power gate mode to be enabled, since it was available on older code, it's possible for motherboard vendors to rely on older firmware to retain support. Think of it like continuing the support for non-K overclocking or AVX512 on Alder Lake processors.
The tuning process with PowerGate is actually very similar to how we did it in OC strategy number 2, with one major difference. Instead of relying on the VF curves, we set a static output voltage for the VCC-IA voltage rail and then use an appropriate VR load line to determine the voltage in high load scenarios.
The easiest way to choose an appropriate VCC-IA voltage for power gate mode is by first choosing the maximum voltage for 1T workloads, then afterwards configuring the VRM load line to stabilize NT workloads. In this case, we can simply set the VCC-IA voltage to 1.45 volt, which is equal to the P-core DLVR voltage limit, and about 50 mV more than the E-core DLVR voltage limit. Now we can test the single thread stability similar to how we did it in OC strategy number 2. With 1.45 volt static voltage for the P-cores, I could increase P-core 0 and 1 to 5.55 GHz and P-core 2 to 5 to 5.6 GHz. It's especially surprising that P-cores 4 and 5 were a lot more stable in PG mode than in DLVR mode. With 1.45 static voltage for the E-cores, I achieved the same 5.1 GHz overclock for both E-core clusters, as there's no additional overclocking headroom compared to DLVR mode. The crucial part of all-core tuning is managing the output voltage with an appropriate VR load line. The process to figure it out is pretty simple. Set the turbo ratio limit for all-core to the maximum per-core ratio limit, then check stability. If it's unstable, increase the VRM load line. If you hit TJ max, reduce the VRM load line and or reduce the turbo ratio limit. I found that there was no difference between DLVR and power gate mode for the all-core turbo ratio limit. So I could set it to 56x for the P-cores and 50x for the E-cores. However, there's a difference in that the effective all-core frequency is higher because P-cores 4 and 5 can now run at 5.6 GHz instead of the 5.3 GHz with DLVR mode. Upon entering the BIOS, the CPU boost frequency with one active P-core is 5600 MHz. The average boost frequency gradually trails off to 5583 MHz when all P cores are active, and to 5250 MHz when all P and E cores are active. In single-threaded applications, 4 P cores can boost to 5.6 GHz and 2 to 5.55 GHz. Every E core can boost to 5.1 GHz. We reran the benchmarks and checked the performance increase compared to the default operation. While Power Gate mode isn't officially supported anymore, my experience proves it has a place in Intel's overclocking toolkit for regular overclockers. For some reason, PG mode suddenly enabled the overclocking headroom for P-cores 4 and 5, which added extra multi-thread performance. The performance difference with DLVR mode isn't huge, but it's a lot less effort to get to the same results. The geomean performance improved by another 0.24 percentage points, and we get a maximum improvement of plus 58.09% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU P-core effective clock is 5,578 MHz, and the average CPU E-core effective clock is 5,000 MHz with 1.368 volts. The average CPU temperature is 95 degrees Celsius. The average CPU package power is 284.5 watts. When running the OCCT CPU SSE stability test, the average CPU P-core effective clock is 5,575 MHz, and the average CPU E-core effective clock is 4,984 MHz with 1.376 volts. The average CPU temperature is 94 degrees Celsius. The average CPU package power is 261.2 watts.
All right, let's wrap this up. This was the very first time I had an in-depth look at tuning an Arrow Lake system for a daily overclock. And it was an interesting journey with ups and downs. On the upside, it seems that this Core Ultra 5 245K had quite a lot of headroom when it comes to CPU overclocking. Both the P-cores and the E-cores had quite a bit of extra frequency in them that we could exploit through overclocking. Also on the plus side, it seems that every component can add a little bit of extra performance to your system, whether that's the ring, the D2D, the NGU, memory timings, and so on. Tuning something will give you something in return. On the downside, it does seem that the CPU cores hit some kind of a frequency wall at some point. Even if you lower the temperatures significantly, you don't really get any more frequency out of it, which is a pity because that means that we can't really use advanced tools like OCTVB to get more performance. I kind of wanted to see a 6 GHz Arrow Lake, even if it was just idling at the desktop. But there's still a lot more to learn about Arrow Lake, and I will do that in subsequent overclocking guides. I already have the 265K and of course a 285K setup. Actually, the 285K is sitting on this Apex board here. So if you want to see more Arrow Lake overclocking guides, make sure you stay tuned for that. Anyway, I want to thank you for watching, and of course I want to thank the patrons for the support. If you have any questions or comments, feel free to drop them in the comment section below, and see you next time.